Welcome to Study Loop.
Hello everyone, today we're doing chapter 23, problem 52, and this problem asks us to draw the product in each of these reactions. So let's look at A first. So in A, we have some sort of carbonyl group with an alpha halide, and then we're adding some sort of reagents that will promote elimination. So we know lithium bromide will dissociate in solution to lithium plus and Br minus, and Br minus can act as a nucleophile to cause an elimination reaction to occur, in which it will pick up one of these protons, making a bond, and then the sigma bond will break to form a new pi bond. So for A, we could say that we're going to get an elimination product, and when you make a bond, you break a bond, that bromine will fall off, and we will form a new elimination product in which you will form both the E and the Z isomer. So here we drew the E isomer, so we'd also have the Z with these two groups on the same side. So for B, we're adding heat. So what we know about heat is that it promotes spontaneous decarboxylations of alpha carboxylic acid group. So if we see here, like this is a carboxylic acid. So let me actually just blow this up a little bit. Just get rid of this and just blow this one up. Yeah, that's better. So now we see that this carboxylic acid is actually alpha to a carbonyl group. So when you add heat, the lone pair electrons in this oxygen will go to form CO2, making a bond. You make a bond, you break a bond. So this bond is going to go to this carbon nucleus and pick up this proton to neutralize it. So for B, you can say that you're going to form a spontaneous decarboxylation product using heat. And only for carboxylic, because we have another carboxylic acid here, but there's nothing alpha to it to promote the spontaneous decarboxylation. Nothing is driving this reaction on this carboxylic acid. It's just happy to stay as is. But here, because it's alpha to a carbonyl group, it promotes it to go through that spontaneous decarboxylation to form two products and increase the entropy of the system. So now you have products for B. Now in C, what we have, well, let's draw C out so we can actually visualize it. So for C, we're starting with 1, 2, 3. So 1, 2, 3. We're starting with this group, and we're using LDA, which is a strong base, to deprotonate this alpha proton. And then we're adding an alkyl halide group. So we're going to add those two carbons off this alpha position because we're forming a nucleophile and these are electrophile. So we'll have an SN2 nucleophilic attack to add those two carbons here to form product C. Now for D, what we have is an alpha halide, and we're reacting with a strong nucleophile, just being this amine group. So what we can actually have is just a simple SN2 backside attack with inversion of stereochemistry here. So for D, we just have a simple nucleophilic attack, SN2 nucleophilic attack with inversion of stereochemistry. So you have carbon, and then those two carbons here. And this nitrogen is going to have 3 bonds. Maintain neutrality. And this gives us product for D. Now in E, we have LDA, and it's again this alkyl halide, but now we have 2 alpha positions that have 2 types of alpha carbons. So remember, LDA is big and bulky, so it's going to give us, it's going to deprotonate the least sterically hindered side, and that's going to be the right side. So this is going to give us the kinetic product. So we're going to deprotonate this right side to make a carbanion, which is very nucleophilic and reactive, and it's going to react with this electrophile to get 2 carbons at this addition at this alpha position for E. So now we're going to add those 2 carbons at that alpha position for E. Now in F, we have some sort of acid-catalyzed halogenation occurring. So we're going to add halogens to the alpha position, but the only alpha position that is available that doesn't already have 4 bonds non-hydrogen bonds is the right side. We have one hydrogen that can be removed, so we can replace that hydrogen with bromine. So for F, after step 1, we're going to have halogenation occurring at the alpha position. And then we're adding the same reagents in. We determined that those reagents are leaving group reagents, or sorry, what we could call elimination reagents. So we're going to have an elimination reaction occurring in which this proton here is going to be deprotonated by this bromide ion. We'll have deprotonation, making a bond. You make a bond, you break a bond. So you form a new pi bond. You make a bond, you break a bond. So the bromine will fall off to form the elimination product in F, which is now this product here. And now in G, what we're adding is excessive halides to this terminal carbon, alpha carbon here, and then we're using this this is occurring in a base catalyzed manner. So what we can see is that we're going to have some sort of haloform reaction occurring in which the 3 hydrogens at this terminal position are going to be replaced for iodines, and then we're going to have hydrolysis occurring from using this base. So you can see in G, after the iodines are added, we'll have 3 iodines at this, replacing the terminal carbon hydrogens, and then we'll have the OH coming for hydrolysis at this electrophilic carbon to kick off this good leaving group now. This is all for G. And now we're going to have our products being this haloform being formed with an oxygen attached to the acid and CI4 or CI3H. So we're forming O- and CI3H or CHI3. And now we are on H. So on H, what we see is that we have the cyano group, and we have a strong deprotonating agent. So H- is not stable. H- would rather be H2, so it's going to pick up an acidic proton. And what we know is alpha to cyano groups, just like alpha to carbonyl groups, these protons are acidic, so it can deprotonate that to make a carbanion at this alpha position. And then what we have a few carbons down is a good electrophile, so we can have intramolecular cyclization occurring to form this our product here, and then we're going to have 1, 2, 3, 4, a 5-membered intramolecular ring being formed off the cyano group. So for H, we can draw that 5-membered ring that we formed, and then we're going to have the cyano group. Now in I, we have same conditions as in G, but now the only difference is this is, instead of a terminal carbon, where it's an intramolecular carbon, so there's only 2 protons. So after we replace these 2 protons with bromines, even if this OH- were to attack, there's no good leaving group because this only has 2 halides and not 3 like this terminal position. So we actually can't go through hydrolysis in I. We can only add or substitute these 2 hydrogens for the 2 bromines, and then that's the completion of the reaction. There's nothing further that we can do, unlike when it's a terminal carbon when we're adding these halogens. So when it's a terminal carbon, we can go all the way to haloform formation. However, when it's an intramolecular alpha carbon, we can't form haloforms. We can use halogenation. So you're just going to replace those 2 hydrogens with 2 bromines. And that will be the completion of that reaction. And last but not least, you have sodium iodine. So typically iodine is a leaving group, but here it acts as a nucleophile because it's I-. So you can have a simple SN2 backside attack with this electrophile being another halide. So you're just going to have halogen replacement, or changing the identity of your halogen from chlorine to iodine. That's a product for J.